It's Tuesday and... No, it's not, it's Wednesday, and it's something totally different. Eddy has sent me, very kindly, a Heathkit Grid Dip meter, the GD1 which comes from 1972, and so you've got the complete manual of assembly, because these were available in kit form, already built, and the instructions for use, and a few of the graphs you could do with. One of the things which, when I did my training in the 70s, and I have never owned a Grid Dip Oscillator, but when I did my training in the 70s, of course I was tutored on them, and I have to admit that it's called a Grid Dip Oscillator because the grid of the valve is what is you're dipping to get that reading. I'm looking for the circuit diagram. There we are. And this uses an EC92 valve. So that, in European speak, is going to be E, 6.3 volts, C, triode, and then B9A base and type 2. So I know the Americans use all this 686 and all this kind of stuff. In Britain, it's that. So if it was a different type of heater, supposing it was 1.5 volts, it would be DC92. If it was intended for television use in a 300 milliamp heater chain, it would be PC92. So you get the same valve with the different prefix. So EC92, 6.3 volts, and we have a power supply which produces 6.3 volts to run that heater, and with 145 volts, which is rectified through a solid state half-wave rectifier. A couple of capacitors which have probably seen better days by now, and then we've got the valve. Your coils plug in for the different bands it can work on, and they're provided in that box. Then there's a meter and there's a headphone jack. Voltages may vary by 20%. Well, I'm not going to go inside it unless it doesn't work. That's easy. So what can you do with the Grid Dip Oscillator? Well, one of the things which we have to keep doing is adjust radios which have got multiple crystal synthesizers. So let's see if I can find an example kicking about. Going to start to make sure we've got a modern enough plug with the shrouded pins. We've got a 5 amp fuse. I prefer a 3, but at least we have got a fuse better than 13 amps before I plug this in. So, because solid state ones have the advantage of being more portable because you can run them on batteries. Okay, so we're plugged in. So the first thing we can do is we can check frequencies with it. One of the things you can do, apart from checking the frequency of a transmitter or for harmonics on a transmitter, like we use the spectrum analyzer for, one of the other things you can do is have a coil. Now I've got a cheap aerial we're going to do a test on. It's a CB aerial from PNI, and it's a really short one. And I don't know whether this is going to work for 200 yards or whether it's going to work for 6 miles. We don't know. I don't give much faith, but we can see its resonant frequency, hopefully, without using an expensive analyzer. So the first thing I'm going to do is we're going to put a lead onto our frequency counter on the test set, and we'll demonstrate this as an oscillator. I think it goes up to 200 megs. Let's have a look at the specification. Okay, the specification is not at the beginning. Specification, no, it's 1.8 to 230 megs. So that'd certainly cover up to your 2 metre handband and beyond. In the UK, our next handband from 2 metres on 144 megs, 145 megs, is the 77s band in the 430 to 440 region, so it wouldn't cover that. So it's HF and VHF. In America, that would cover they've got a 220 meg handband, which we don't have here in the UK. So, I've got a 27 meg cheap walkie-talkie here, one of the realistic 1006s, 50 milliwatts, and we know it transmits on 2779125. So that's the first thing. So as an oscillator, we'll probably be able to hear this if it's working. So I'm going to select a coil for the 27 meg band. (14 to 37 megs). Assuming that's been correctly written. Perhaps I ought to check. It's a matter of trying to do this speedily and but accurately as well. Right, anyway, so we'll plug in this coil. We'll switch that on, and as an oscillator, as we tune around, so that's kind of spot on. And what that tells us, if we were on the right scale, which we are, it actually tells us we are on 32 megs, which we're not. No, so the calibration is not quite where it should be. But you can see that because it's emitting effectively a small amount of transmit power, then it's causing this to quieten, as we would say, because it's an FM receiver. We can tune around there. Now we can read off roughly the frequency it's transmitting on. It's receiving on, so should I say. So the opposite would apply if I go into diode mode. I'll pull up the arrow and we'll press transmit. So now you're going to use it as an absorption wave meter. So press transmit. And it doesn't work. And we've got a dirty switch. No, we are not having any joy with that. So it looks like it's time to take it apart. I honestly didn't think it was going to work. So the calibration's slightly out. The this isn't going, you know, at 27 megs, this isn't going to read out the frequencies. I mean, if you look how wide this is, it's not going to say you're doing 27. Well, on the wrong camera again. It's not going to say you're doing 27.79125. Look at that calibration. You know where we are with 27 megs. You know, it's what? 26, 27, 28, 29, 30. You know, it's you've only got a rough idea that you're on the band, but that's usually what you want, what you're looking for. What I was going to say to you is, we'll look at the harmonics coming out of that radio. What was coming out at 54 megs are the harmonics, you see. So I'm not sure we're going to get. I don't know whether the meter's not working, or I don't know whether the actual device isn't working. So I think a sensible thing to do would be plug some modern mono headphones in, but I don't know whether they're supposed to be high impedance or not, so this is going to be an interesting thing, because the only headphones I've got are 8 ohms. So pause the video. So there's a look inside it. So we've got a power supply, smoothing capacitor, meter, exposed on and off switch. Under the side of the valves you've got the resistors and capacitors, which are... Why is that split? Interesting. Yeah, so it's been nicely put together. So we're going to have to go through a bit of a fault finding procedure. So what does it say? So it does. I didn't realise it had an on and off switch, so I could see from the inside that the sensitivity control has an on and off switch. So that helps safety a little bit. So what are we looking for? We're looking for 75 volts on pin 1 of the valve. I'll just switch it off and just check where I am with the valve pins. Yeah, it wasn't obvious that. Switch it back on. So either that's pin 1, that's pin 1. It's a bit high, but the power's nevertheless there. Let's see what we... Well, that's the initial test. That's... how to calibrate it. So we're going to have to go through that. It should be remembered that the GD1U has not been designed for laboratories for applications requiring a high degree of accuracy. the GD1U does not have the same degree of accuracy as the laboratory standard signal generator, which is what we're normally using, many of which can be used as secondary frequency standards. Calibration errors of up to 5% can be expected. However, except for specialised users involving higher accuracy, this instrument is invaluable in applications such as outlined in the manual, as well as other too numerous to mention. It's provided with a ready calibrated dial, and this dial is sufficiently accurate for most applications. Now, it's about 5 megs out, which isn't accurate enough for me. So we need to do so. We might have to unglue this dial, and without breaking it. So we calibrate it with we can calibrate it with a signal generator. So we can do that very easily. We could also plug it into our little amplifier, which may help instead of headphones. Certainly help when doing a video. Then it tells you at what point you're going to be sticking that dial on, which of course is already stuck on and in the wrong position. Well, I want to use this as a marker oscillator. I'm going to want to use this at 10.695 to do IFs on some of the radios, because our marker oscillator only does 455 and 21.4 and 10.7. So 10.695 would be a very useful thing for this to do. So I think what we're going to do is see if we can set up 10.695. So we'll select a coil. So we'll put that one away. And we'll select the B coil, which is the one which, oh yeah, band B. No? Yeah, band B. Might be putting some Dymo labels on these. Other brands available. So we want this to produce 10.695. So if we turn this dial to about there, every time I use this, I'm going to have to check this with a frequency counter. But it's still a useful tool. So let's have a look. Let's put picture in picture on, and we'll look at. Okay. So I'll move this across. We'll have a loose coupling. So hopefully we can alter this. So I've got it at where we think would be 10.6, 10.7, and the frequency counter is saying 9.4. So let's make sure we're not on a false plate. So 10.694143, that kind of position. is going to be absolutely fine for setting up those IFs. So we've done it, but the scale says that we're spot on 12. So this is being put on in the wrong position. So we're going to have to somehow. I'm going to turn this off. Anyway, it's proving it's selecting the frequencies we want. So how's this done? Because I can't actually see, there's a grub screw down there. Okay, it's pushed on. So, and there was a grub screw. I can't speak. There was a grub screw, but it was kind of inside the top. Okay. So we need to carefully. Scared of this breaking. I mean, the fact that the scale's inaccurate wouldn't have mattered in that application because we're using it with a frequency counter anyway. I think we have to release that from underneath. There we go. Right, next we need to put this back on and make sure everything's in the right position. Just waiting for the valve to warm up. Okay, that'll do. So I need that dial to be there. Now then, let's see with the other coil whether our 27 meg CB is anywhere near so that's the right coil for that. So we're going to, I'm not going to put the knob on yet, so we'll now turn this for, it's probably there. And look at that, it's just under the 28. And that, of course, is 27, oops, I'm on the wrong one, 79125. We tune around. So we've got it calibrated now. Oh, that's a step in the right direction. We'll put the knob back on, and this time with the grub screw. I can pretty well bet that this has never been calibrated as accurately because we're using laboratory instruments, so that's great. So we can certainly use it as a oscillator for setting frequencies. Now, does this go down to 455 to do the other IF? No, it doesn't. Additional coils to go down to 350. Do we have any of those additional coils? No. So we can't use it on 455 IFs. That's fair enough. At least we know where we are. So why wasn't I able to hear this into my headphones? Well, I'll tell you what, before we start messing with that question, we'll go back to that aerial that I brought in. These can probably go back together now. I think we're sorted, but I just want to prove that it's working in diode mode. And I might have to read up what that actually means. Where did I put that aerial? So is it possible for us to go parallel with this loading coil like that? Let's just come out again. And see what the resonant frequency is of this. Oh look, we've got the meter working. Let's just come out again. Now clean that switch. So now So we're now around about the 28 megs. We can see so according to that is 28 megs broadside into that loading coil, which of course is what it is. How handy. It's Tuesday and no, it's not, it's